Hello and welcome to Inside Exercise. I'm Emeritus Professor Glenn McConnell from Victoria University in Australia, but I'm currently a Danish Diabetes Academy visiting professor at the University of Copenhagen. Inside Exercise brings to you the absolute who's who of exercise research. So exercise physiology, exercise metabolism, and exercise and health. And the idea here is that I want to have you getting your information from the experts in exercise rather than influencers. Now, talking of the University of Copenhagen, I've just finished a very interesting chat with Professor Lars Nybo from the University of Copenhagen. He's a real expert in the environmental effects on exercise, performance, and metabolism, etc. So we talked about altitude, but specifically we focused on heat, the effect of heat on exercise performance. But also a large focus was talking about how you cannot always assume that findings in the lab can be applied to the real world. So he had several examples of this that were very interesting and very important. Lars is not just a top researcher, but he's also a top cyclist. And quite recently, he actually did a 1 hour time trial and did 45.7 kilometers per hour, which is remarkable, about 29 miles per hour. I really enjoyed talking with Lars about determinants of performance, the effects of heat. Also, we talked about cross-sectional area, so coefficient of drag, etc., and the effect of watts and watts per kilo on your performance. I found it really interesting. I think you will too, so stick around. Hi, Lars. Thanks for coming on. Welcome to Inside Exercise. How are you doing?
Great, thanks, and pleasure to be here. I'm a fan of the concept, and since you are interested in the same areas as me, exercise, physiology, and cycling, I mean, I think it would be a nice opportunity to talk about those areas.
Yes, indeed, and thanks for coming on at late notice. I only asked you last week. Yeah, so we're going to talk about environmental physiology, and what results and lessons from the lab versus real life, which is interesting. So saying that what you do in the lab doesn't always necessarily relate to real life. But I can't help asking, especially because I've written for you before. You're a very strong cyclist, and someone on Twitter wrote that you'd recently broken a hour record, so 45 kilometers an hour. So for the people that haven't heard about metric yet, it's about 28.5 miles an hour. Is that correct? That sounds unbelievable.
The conversion I can't, but you have to divide by 1.6 or something like that. So yes, but it was. It was an old concept, this hour record and so on. And then I had a friend who rode like 43 and some on and it has to be an ordinary bike, so it's without disc wheels. It's just my plain road racing bike and so on.
Okay.
And then I had it as, so to say, a goal of 45, and then we have some roundabouts around. And then you can say my personal interest, actually, I think the way that I got fascinated by physiology, and in particular exercise and endurance physiology, was through cycling, and I mean this fascination for that. So then I had it as an aim, and I actually went 45.7 kilometers because when you have to have everything with you and so on. But it was quite fun and so on. So that's more of a hobby. And you can say I used to race in you could say national elite in my younger days, and then I did some master races afterwards and so on. So and as I think it was Michael Joyner who also had a disclaimer that everything I say here is my personal. I don't think I have to say so. I'm here as a researcher, but also as a private person. But I think that what we need to bring to the table is, of course, the idea of what is the highest level of evidence that we have, and that is, of course, our science-based knowledge. And then we can have the individual observation, and sometimes our interest into science can be driven by that. But in relation to this, I mean, you get more and more fascinated by what happens with aging the older you get. And I passed 50 last years, and then it's funny to look at that. And one of them asked if I can break this record in optimal conditions. And then you had to say, okay, all my analyses show that you lose approximately 0.3 of a kilometers per hour per year you age. So then you have to find either technological development or more optimal conditions. And again, actually back to some of the things that we have to discuss. I mean, the day that I wrote that, it was like 24 degrees or something like that. And you can say although that's quite hot for Danish conditions, you could find hotter conditions. And then you
Mm-hmm.
would say, oh, but doesn't heat hamper your performance? And that was one of the observations that I had. Yes, if we test people in the lab going, let's say 30 or 35 degrees Celsius, there's a lot of studies. You do a simulated time trial in the lab, then you have a reduction in power output by somewhere between 6 and 10%, depending on the humidity and if you have wind speed on you. But the thing is, if you go outside and you race, then you actually go faster because the air density is lower. Plus, you have much more convective heat loss when the wind speed is high. So all of your sweat will evaporate. Whereas if you have very low wind speed, if you have no wind at all, but even if you have a ventilator that provides like 3-4 meters per second, then it's less than when you go out and you do 45 kilometers an hour. Then you have, even with zero wind, you have a lot of wind speed that facilitates evaporation. So you have quite different conditions. And that was my point to you, that that is one of the mistakes that we have made in the exercising lab, is that of course we like to have it in the lab because we can control everything, we can measure everything and so on. But then you go into real life and then it's 35 degrees. We have not been able to simulate that significantly or well enough.
Wow, I mean,
Another
I understand
observation.
that. Sorry, I understand that concept, of course, that especially outside, you're getting so much more wind speed, like the wind passing you at the same speed you're going, basically, and getting convective heat loss.
But you also
But even
benefit
at
from lower air
35, yeah, the lower
You also
air
benefit from
density.
lower air density. I would think that the optimal temperature would be like slightly lower, because when you go in 35 degrees, your skin temperature will be around 35. So it's approximately the same. And then you don't have any dry heat loss. So you would say the optimal temperature would be around maybe 30, because then you would still have a gradient. So you could rely less on, you would get less of a cardiovascular stress. But our observations from when we did time trials in Qatar 1 hour was that when people were acclimatized, they only lost 2% of power. Whereas if that was in the lab, they would have lost 10. So that was just for the temperature. But for those 2% lower power, they went 2% faster because the air density was
Air
lower.
density.
And temperature actually also affects rolling resistance a little. But again, it's somewhere where the interpretation from lab results into real life is not one-to-one. And some of my research has concentrated about that, because in other concepts, it's like with thermal stress, we had observations the other way around, that we have some observations that in real life, your what we call motor cognitive performance, your ability to do tasks. And whenever you do a task, unless it's pure philosophy, there's always a cognitive component and there's always some motor component. Speaking, writing, whatever, there's a motor output. But in these types of tasks, we observed that people make more mistake in real life. But when you do it in the lab, then you could have a lot of conditions where you didn't see any decrement, either because the tests were not sensitive enough, or because the exposure time was, I mean, in real life, you're exposed for a whole working day, whereas and so we actually developed some tasks and tests that were more sensitive for that. Some of the work that we did with a recent PhD student, Jakob Pihl, who was here, and we developed this test battery.
Can we get back to that? Because I want to just talk a bit more. So when you said about the 35 degrees, that was what I thought. It's like, hang on, what about skin temperature? So are you backtracking on that slightly? Are you saying maybe 30 degrees? This is Celsius, of course. Because, I was surprised that you said at a time trial at 35 degrees Celsius, you could do better than at, say, 22 or something.
You do better in terms of speed. You do a slightly worse in terms of power. But since the thing that determines speed when you go on a flat road is power per CDA. So it's actually your coefficient of drag relative, or your power relative to that. It's quite clear that if you go uphill, then it's power to weight, and since you don't change your weight, you will not benefit from a faster. So I think that if you did it and you would have to evaluate performance, you should discriminate between whether that is performance in an uphill ride or whether it's on a flat road. So I basically normally say that if we want to test the ability on, I mean, because cycling is still defined by how fast you go and not power meter, even though a lot of people, they look at their power meters and then they use that as a performance indicator. But I mean, and we also sometimes do that. But the on flat road, I usually say that it's your power per CDA, which is determinant.
Can we just
of how fast
make sure people are clear on what CDA is, just for people that aren't.
It's combined of the coefficient of drag and your front area. So if you have a large front area, of course, you have more air resistant. On the other hand, it's also dependent on your shape. How well do the air slip away? So let's take an example. You have a round ball that will have a given area. It can have a much lower CDA if it has a tail. So that's why you design drags, because if you don't have the tail, then you will have a vacuum behind you, and that actually drags you. So it's a measure of that. And we can measure it in a wind tunnel, but we can actually also modulate it. So if we on an outdoor level have the speed and your power, then we can calculate it, given that we estimate the rolling resistance and so on.
Okay, so just to put that together,
so
then
so to say, it's a measure of how aerodynamic are you.
Yes. So it's your watts kind of divided by your drag, that determines how fast you go. And again, I guess that's something that on a flat road. And I guess I guess that's something you can't measure on the lab. Well, you can do it wind tunnel, but you can't with
you can do that. And that's a funny thing. And that was my observation from first my single point, but now we actually have data to support it. So we also actually have research data to support that. We just did a study where we measured a range of very trained cyclists, 12 all, and we actually did a study where they were exercising for 6 hours. And then if we just measure how fast can you go for a short time trial, if we have their power output from the lab. So we have an incremental power output, and they measured it while we do oxygen consumption and so on. The R squared value is 0.22, which would say that if I know their power output in an incremental test, even on their own bikes, it's not on an ergometer, then the translation would probably be even worse. Then I can, so to say, foresee 22% of how fast they will go. If I know
can I just clarify
power,
again? Sorry, just so make sure everyone's on the right page here. So you're talking about, when you say increment, you're talking about like a VO2 max test, for example. So you start off easy, get harder and harder, and you get to their peak power output. So the highest power they get at the end of the test. And then you're saying when you look at that compared to their time trial, out on the field, the correlation, the R squared, the speed is only 0.29. So it's very poor correlation. 0.22. Okay.
And then you could say, okay, no, but it's, if you then divide it by weight, so instead of having power output in absolute terms, you have it per kilo body mass, then the correlation disappears at all, because on a flat road, it's your absolute power is more important than your per weight. It's quite clear that if that was uphill riding, it would be a total different picture.
Yeah, can I just make sure people are good on that as well? Because people often think about, as you say, VO2 max being as your maximum aerobic capacity. And the interesting thing is, I remember, because I had David Costa on here, I did my master's with him. We used to, if we're looking at, say, a cyclist on the flat, we didn't used to worry about the VO2 max in mils per kilogram per minute. We would not divide by body weight. We just say, what's their max in liters per minute? And same, I guess, with a rower. But if you're talking about a runner where you're carrying your body weight, you would always convert it to mils per kilogram per minute. So I guess that's the same sort of thing you're saying there, that if it's a flat ride, time trial, you don't really care about, you just care about their maximum watts and their drag, their coefficient of drag, etc. You're not worried about their body weight so much. But if it's hilly,
because you could say the body weight will only increase your rolling resistance slightly. So you could say 10 kilos more body weight, all other things equal, because it's quite clear that if you are heavier, then probably your area is also bigger and so on, then it affects other factors. But the weight in itself doesn't play that big of a role on a flat chest time trial. And I mean, we can also use that from observations, just observations of nature. I mean, bigger riders, time trialists are probably, usually they are bigger, but you can say there are some small, and the reason why some of the small can compare to that is, of course, because the small riders also have a smaller CDA. So if you are a very little rider, Remco Evenepoel, Jonas Vingegaard, who won the Tour and so on, if they can be very compact because they are so small, then they, of course, their power to CDA ratio also becomes high.
I mean, how do you end up with? I can't help thinking about Wout van Aert. How do you end up with? I know it's a bit of a side issue. How do you end up with someone like that, who can win sprint stages? It just seems to, again, maybe this is an example of measurements in the lab not meeting real life, because surely to goodness, if you did all your measurements in the lab, you'd say that he couldn't win sprint stages plus sort of climbing stages plus time trials. I mean, you wouldn't normally.
I would actually take it the other way around. If you tested Mark Cavendish in the lab, people would say, oh, he would never win anything because he has his strength is not absolute power, neither in terms of anaerobic power or aerobic, but it's his anaerobic power in relation to his CDA. So when he sprints, he's able to sprint in a very low position. So he can actually do fast and so on. But the thing with, let's take Wout van Aert, is that he has a very high both aerobic capacity and anaerobic capacity. And then you could say his anaerobic, his sprinting power is not as high as, I mean, if we compare him to some of the track sprinters, I mean, they have peak power of like 2,500 watts or above. I mean, some of these Dutch guys, I mean, he's lower, but the sprint at the end of a stage race or a cycling race is on the top of an aerobic effort. So you could say that he has a very high aerobic power relative to the CDA, means that he can sustain and he can, so to say, preserve his, what in cycling term is called W, I mean his anaerobic capacity. He has that intact when he starts, or not intact, but he has it when he tops the sprint, and therefore he can still do that. I would guess that his peak anaerobic power is less than the very specialized sprinters also on the road. But in those stages, races where the lead into the final sprint, which is only 12 seconds at the end of the race, if that has been very hard, I mean, then some of the real sprinters, they have lost some of their W mark. So they have lost some of that capacity. And then you could say that is something which is quite characteristic from some of the riders coming from the cross cycling.
Cyclocross.
Yeah, because you could say the if you only have a high aerobic capacity, so if you're very strong in that perspective, so let's take some of the biggest time trials, they will not be able to be competitive in cycling cross, because in cycling cross you need to be able to also sprint up of the very small hillings that there are. So you have to be able to have a high aerobic capacity as well as anaerobic, and therefore some of these riders are very excellent in those types of races that also have those demands in cycling race. Whereas the pure sprinter, they are not aerobically not fit enough to compete in cycling cross, and the other way around. If you only have a high aerobic power but you are less strong in the anaerobic, then you will lose too much time in all of the accelerations that characterize that sport.
And that's the amazing thing that you think that these people are doing these sprints at the end of a 200-kilometer stage where they'd probably be averaging.
But again, that's something that we have neglected. So when we do time trials, and I also saw your discussion with Kogan where you said, oh, there was all these 26 different measures of lactate threshold and so on. We always do these very continuous protocols in stepwise, and then you can, and can we determine this? But if you have cycling in real life, it's actually an intermittent sport. very extreme in cycling cross, very extreme on flat roads where you have accelerations up and down and power, even if it's a time trial. I mean, the power curve is not that flat. Whereas if you go uphill, it's more steady. But even in uphill cycling, you always go above the threshold and below the threshold. So you actually, your voltage is fluctuating much more. And then you could say from a physiological point of view, of course, you have a much broader reliance that all your fiber types are equally trained, where if you test people at a very stationary fixed load, then you don't get a true response. So I would say, again, one place where we, so to say, have failed to mimic true physiological exposure. Also, your discussion with Niels Erdenblad in terms of is glucose ingestion actually saving glycogen? Again, if you test that in a protocol where you do a very stationary power output, the old studies by Coyle, I mean, there's no glycogen sparing effect of ingesting glucose. You spare some liver glycogen, but muscle glycogen is actually broken down. But I would guess that if you have real life fluctuating power outputs, then you would see a bigger effect.
That's interesting.
So we need to, in some terms, to be better to mimic our protocols in the lab, or at least understand why is it that some of the things we observe in real life are different.
Yeah,
So
as you say, it's easy to control that way. But yeah, I remember, I think I might have mentioned it in Neil's chat as well, that the classic old study, J. Mark Davis did carbohydrate ingestion in one trial and placebo in the other with intermittent exercise. And there was some sort of sparing. But again, you know, how
for sure. They did that.
Yeah, often they keep it, you know, like it's perfect the whole way along. You know, it might be 15 seconds hard, 45 seconds easy. But as you say, that's not real life either. So I'm interested in something we talked about. Well, I have to say, it's a bit weird. I'm actually in Copenhagen, as you know. I'm just telling the listeners and viewers, we're probably about 100 meters away from each other. Yeah. So we were talking in the corridor the other day. I'm just not set up. I don't have like two cameras going. We were talking in the corridor the other day, and you touched on it with this sort of 6-hour study. I know we're going to focus on some other bits and pieces, but why don't you just talk about that? That was pretty interesting. You were trying to sort of make it more mimicking a real life sort of 6-hour race, I guess.
Yeah, because you could say some of you could say in the old days, I mean, could only control and measure power output in an ergometer or in the lab, but whereas today you can actually measure it in real life, so you can actually use that as a measure. Of course, we are always afraid, oh, what about variability? But that's how real life is. I mean, also if we have to temperature, which I'm interesting, it fluctuates. But what we did here was we utilized the ability to combine, you could say, physiological lab measures with more ecological exposure. So what we did was we took our oxygen equipment, etc., and took it out to this old aerodrome, which is now closed and is open. And then there was some of these hangars. So we borrowed one, and then we put our oxygen equipment in there. Then we tested people for 10 minutes at the intensity that in the lab elicited the maximal fat oxidation. So we did this classical where you do in steps and you measure RQ and your oxygen consumption, and then you can calculate or you can estimate your fat and carbohydrate combustion. And then we had them exercise on the intensity that elicited maximal fat oxidation, 10 minutes. And of course, we can also use in the velodrome, inside on stationary bikes, on their own bikes, put on trainers, and then we measured oxygen consumption. Then we took them out, and then they did in total 6 hours of simulated bike racing. So first they did a peak sprint just to get their peak power, which was in these guys on average just below 1400 watts. And then they did a 5-kilometer time trial, one round on the aerodrome to test their aerobic power. Then they did 1 hour and 45 minutes of simulated racing, paced by a pacer of 42 kilometers an hour. And then they also did some echelon riding to simulate the race. But on average, and what was very nice was we were actually able, because they were paced in these, to control it. So when they did which was, so to say, to simulate when you ride in a peloton, the long tours, other teams are dragging, you're putting there, then they had a mean power output of around 3 watts per kilo. So 230 kilos and so on, and quite funnily equal to the intensity that elicited their maximal fat oxidation. And then they did 20 minutes where they did echelon riding, and there the power output was approximately 100 watts higher, so 4 watts or so per kilo. And then they did more echelon riding, and then they came in again, did a peak sprint, 5 kilometers all out, 1 round, another 2 hours, tested our 4 hours, and again after 6 hours.
Is this on the stationary bike, yeah? So you said they came in.
No.
I thought you said they rode around on the velodrome. And then they
just came in for a blood sample and did a peak sprint, and then they did 1 round. So it was all of that was in ecological settings on real life moving bikes and so on.
Mm-hmm.
And then at the end of the 6 hours, then we took them on the stationary bikes and measured oxygen consumption again.
Mm-hmm.
So that was the setup and so on. And the thing was, we wanted to study individual fatigue patterns and resistance to fatigue. Because there are some observations from pro cycling that the best professional cyclists, they are very fatigue resistant. So at the end of these very prolonged efforts, which you could say 6 hours is what you see in the world championship in all of the classics and so on. Whereas if we do studies in the lab, 6 hours is really long on a stationary bike. So we wanted to have that kind of very prolonged so on, but also in settings where it mimicked the intermittent nature you do when you do the echelon riding. You do your turns, then you do maybe 500 watts, then you are back on the wheel, then you do 250 and so on. So we get this kind of fluctuating. But some of the interesting observations was that even though we gave the subjects 90 grams of carbohydrate per hours. So over these 6 hours, they got around 550 grams of carbohydrates. Then their fat oxidation increased. So it actually was higher than it was when we tested in the lab in an overnight fasted. So even though they ingest that, they still combust around 1 gram on average. And if you then calculate, does that matter at all? It actually, for the echelon part where they had the similar power output, for the peloton drive where they had the same power output, that could actually contribute by more than 50% of their energy turnover, showing that we cannot neglect fat oxidation in these types of very prolonged efforts. Whereas if you do shorter, more intense, for example, if you look at marathon, you could say, what role does it play if you have a high or low fat oxidation? Because, you exercise at such high intensity, you have carbohydrate, fat, etc. Then your total energy contribution from fat oxidation is 20 grams or something like that. But in this intermittent nature, which is mimicking what is going on in real life cycling, if you do the Ronde van Vlaanderen, which one of the big classics and so on, there are lots of these intense efforts. You go up by a healing, you go maximal speed out for 2 minutes, 4 minutes, then you have a prolonged period where you sit in the echelon and so on. And in these periods in between, that's where I think that fat oxidation still plays a role.
There's a lot of interesting stuff there. And you mentioned Andy's talk earlier. I can't help thinking that, there's quite a lot of talk around the place on Twitter, etc., about, you've got to be riding at zone 2. And if you do any sort of higher intensity, it's going to mess up your fat oxidation for the rest of the ride and all this sort of stuff. And Andy was saying there's not really evidence for that. So you would support that as well, that you can do all sorts of high intensity and still burn a lot of fat.
Yeah. And all this with training intensity and zones and different. And so, of course, we use it as practice engineers to find different types of intensities. But your body cannot define a given zone. It sees a stress, and that stress is different if you're a muscle fiber. It sees a certain given of metabolic stress, flux through the system, depletion of internal energy stores.
Duration.
Your heart sees a total different stress. It sees cardiac filling and so on. And you could say basically as human, we have the cardiovascular capacity, which is dependent on your heart's pumping capacity. And of course, that is how well trained is your heart and how much blood runs into that. And then you have the muscular metabolic endurance perspective. So that's why I think that even though you can have all of these different zones and you can have all of these different scores, TSS, whatever you have of all, and this. I mean, for the body, it's nonsense. It sees a given stress, and that is the stress that you as physiologists should at least return to. So it may be that you can understand it on so to say, okay, if you have polarized training, and you can understand why is it that athletes actually do that. They have a lot of intensity at quite low intensities, where you could say in itself, would that give anything? But you could say, okay, if you have that in situations where your energy stores are depleted, or you, because you have that large volume, have a large flux of energy through your beta oxidation or through your mitochondrial, maybe it will stimulate something that may give something. You could say if you only did that, of course it would do more than if you were totally inactive. But if you have a highly trained individual, then it might be the very little, whether it's 10% or 15, or depending on how large your big volume is, of the very, very intense, where you stimulate other systems. You have a much larger stimulation of your cardiorespiratory fitness, your heart, but you also have a larger flux, and you have very large decrease in muscle glycogen. And if you combine these two in a certain sort of mix-up, then you can understand, okay, that might be why the two of them are additive. But I mean, there's never been any of the real big endurance athletes who have dared to only do the intense part. And you could say, okay, because we have quite good evidence that that is very potent. I mean, some of the studies that were done in Norway and Rønnestad and etc. have done is to show that if you do, and we actually also had a study where we did one group, they did 10 minutes of intense 2 times a week. So they did 20 minutes in total, so to say, above peak effort. And they had larger increases in VO2 max than the group who ran 2 hours continuously at 85% of their maximal heart rate. So some intense, but I mean, it shows the very potence of this very intense, and there's very strong evidence for that. Whereas we have quite little evidence. What is it that this big volume has to do? We also published a recent study where we tried to half the volume or reduce the volume to see if that was, so to say, permissive and so on. And we saw that the two groups, when they intensified their training, they did more of the intense bouts, they improved independently of whether they reduced the volume or not. So we don't know what all this volume is, but at least I think that you can understand why it is with lower intensity, whereas you have a lot of it in between, whether you then call that zone 2 or 3 or whatever. But then you would have it in somewhere in between where it doesn't have that much of a stimuli, but it still will deplete your glycogen stores quite fast. So maybe it will not allow you to do the intense parts. So that's why I think there is good both evidence, but also you could say rational between or behind doing the polarized training approach.
Yeah, and part of the idea is to not overtrain yourself, not overdo yourself. I guess if you're just training hard every day.
With some stimuli that may not give you that much, because you have the much more potent in the very intense domain.
Yes, and that's the other thing. Yeah, so the idea that a lot of people are just sort of riding in the middle of nowhere and not doing enough really easy. If you're riding in the middle of nowhere, then
then it would not allow you to
really
do
hard. Yeah.
Exactly.
Yeah, so that makes sense. But I guess I wanted to just bring home again that fact that you were saying, despite the people in your training study doing intense and then easy and intense and then moderate, they were still burning a lot of fat, and if anything more than you got it with their fat max measurement.
Yeah. So when we measured their fat maximum fasted, it was around 0.7 grams or something on average in the group
per minute.
Then when they met up at the aerodrome, and of course they were fed there because they had to do 6 hours afterwards, then of course it was reduced. Normal classic, you get an insulin response, it reduces it. But then they did that, and in spite that they ingested 550 grams of carbohydrate, then the fat oxidation increased, and it surpassed. Again, you can say this about what is equal and what is not different and so on when you get this. But I mean, in absolute terms,
it's definitely not less.
Increased.
Yeah.
It increased to higher level than when they were overnight fasted.
So that's really interesting, and that's it makes sense, but also it's slightly surprising because when they're drinking the carbohydrates, you said 90 grams per hour. I'm assuming that would be maintaining their glucose levels at about the same level as when they started, and the insulin would probably be a little bit not elevated, but not maybe similar to when they started. So you'd think that would be driving glucose uptake, of course, and maybe inhibiting fat oxidation a little bit, but you didn't see that.
No, we actually saw that it increased, and I know that Niels has similar observations when they have done this with 4 hours of simulated in the lab, that it still increases fat oxidation. So there's something when you deplete your, at least
glycogen.
what we think, when you get lower glycogen, then it will increase it.
Exactly. And you mentioned the classic coil. Sorry, the classic coil study. From 1986, we've mentioned a few times on this podcast. But as you said, when you ingest carbohydrate during prolonged exercise at 70% VO2 max and train people, they don't reduce their glycogen use.
But
now,
that's also because they have a steady power output, and they are, so to say, having a constant.
Exactly. And what happens? They maintain.
The thing is with that study is that, I mean, and I actually proved that in a very simple study. I mean, if you look at the blood glucose they have in the placebo trial in COIL study, I mean, they have blood glucose around 3. And when blood glucose arterial goes beyond 3.5, then it starts affecting your cerebral uptake. So my best guess is that what they saw in that was that the ability to keep exercising at the end, I mean, that could also be related to prevention of central fatigue.
It's true.
And
it was
I mean,
very
of course, fatigue is also multifactorial, but I mean, it's quite clear that when you have blood glucose around 3, your ability to keep maximal or keep adequate neural drive is reduced.
It's true, and I was actually quite surprised how low that got. The studies we've done sort of similar studies, like 70% VO2 max to exhaustion in trained people, didn't usually get that low. But yeah, the interesting thing is they because they're ingesting carbohydrate, they maintain they're not affecting their glycogen use. They have higher glucose uptake. They maintain your carbohydrate oxidation.
And of course,
and they
that
go
is higher
longer.
but that's higher glucose uptake, both by the muscle, but also by the brain. So.
Well, it's interesting because I often wonder, we're getting way off track here, and I spoke to Niels about this, but I often wonder, why do they actually fatigue? And I spoke with Mark Hargraves about that as well. Why do they actually fatigue? Because they're going along, they haven't changed their glycogen use. They've got glucose uptake, which is not even plateaued out. The carbohydrate oxidation is normal.
Yeah, my best guess is it's because they get hypoglycemic, and therefore their cerebral.
No, I mean when they're ingesting the carbohydrate. I'm saying, why do they fatigue in the carbohydrates trial?
Oh, yeah, they still fatigue. But at
why is
some stage. But I mean, if you had to test that, I mean, again, that is how we should work. And I mean, I'm also brought up, and I look at mechanisms. So although I'm a fan of that, we make ecological valid protocols and we can mimic what happens in real life. Because I mean, when we study inside here, we're still interested in what is going on outside in real life, in real humans. So we take a small group of person in, and we do biopsies. We take AV differences. Of course, I mean, we're interested in exploring the mechanisms. And I think that if we had to look at that, then we should do some mechanisms where we try to look at, okay, is this a muscular phenomenon? I mean, do electrical stimulation, see how much of a loss do we have of muscle function. And my best guess would be that, and I think that could be interesting, and I'm hoping actually to do some of the studies together with Niels Erdenblad, where we will put people in also an MR scanner to measure to see if we can have a non-invasive measurement of glycogen. But in order to validate that, of course, we will also take biopsies. And I think it could be quite interesting to look there at both, you could say, fiber-specific depletion, but also in his methodology and looking at pools within fibers. Because I think that some of what happens when you get very low glycogen is that you then maybe start also to metabolize some of that, which I call structural glycogen, which has an implication not only as a fuel for the muscle, but also for muscle function. And it may be that is why at the end you start losing some of that, and therefore it start affecting muscle function.
Good point. And also it's a good point there that we spoke about with Niels as well, that obviously the classic Eddie Coyle study in 1986, they weren't able to look at pools of glycogen, or they didn't even look at how much is depleted in fast fibers versus slow fibers. But nowadays that can be done.
But I mean, it's total, and I mean they see really low levels, and that's in mixed fibers. So then of course you could say it's very difficult to see if they have lost another 2-3 of the.
Well, no, it was actually they still had 20% left. That was the weird thing. It's sort of 20%.
No, but you will always have that in a mixed model, and especially,
exactly.
and I also think that's because they did again steady output. So again, if we look at it, and it's like what we do in soccer. I mean, in soccer you can have quite high levels on average. But I mean, if we then look at single fiber analysis, then we can see that some fibers are almost empty.
I want to bring you back to your, you're talking about the time trial performance not lining up very well with peak power output. One thing I thought about with that was it's probably fair enough, right? Because we know that exercise in a time trial, it's not just going to be your VO2 max. It's also going to be what percent of VO2 max you can hold.
Yeah,
so,
but not in this. I mean, because in
threshold.
this one we did 5 kilometer time trials. So I guess that it was like 7 minutes, and if we try to calculate their power output and so on, they were probably exhausting their maximum, at least in the fresh stage where I have these calculations from. So that was in the short, but we're actually going to follow up by 20 minutes because that's a normal test that cyclist riders do, because I mean they want to estimate and so on. So we will try to do it also for a 20-minute time trial, and that is correct. How high a percentage can you? And I like this model. I think it was introduced by Coyle and Joyner. They developed it where they say, okay, your performance power output is always a combination of your VO2 max percentage and your mechanical efficiency, and then of course you have your anaerobic power on top of that. That if it's a very short, then you can add it to it, and then you have all the factors below. But the thing is, then you have your mean performance power, and then you can have, okay, what kind of speed does that allow you to have? And that is where in that step it's very important, what is your position? Because the reason why we see better correlation when we test people in the race position, I mean, if you go in the lab, you will do upright, you will do like you do when you do hill riding,
Copenhagen
because
bike.
there you have your hip angle is a little higher. But one of the things that characterize the best riders, and if you look at all the pro, is that they are actually able also to maintain that power in a very aggressive torso angle. We did that with a new PhD student that I have, but that was then on time trial bikes. We tried to explore that because other studies have shown that when you decrease the torso to hip angle, you go lower and lower, you also lose mechanical efficiency, and therefore you of course lose maximal power output. And then we tested that in time trialists, and it appears that they can actually go quite low. We analyzed the position of the top 10 finishers in the 2021 time trial or so, I think it was, yes. And it shows that all of those finishing in top 10, they sit in a position from 12 degree, your torso compared to flat, and down to 4. So all of the best top time trials, they sit well below what is optimal from, you could say, a biomechanical point of view, where you would have an uprate like 30 degrees, something like that. And I think that because they are so trained in that angle, they can limit the loss of power in that position. And of course, then they get a higher power to CDA ratio. Whereas if you look at the best, some of those who are very good in hills, when they then go to that position, they lose more power. And therefore they are not as good time trialists, although they can be quite good riders in other types of more hilly terrain.
And do these people, sorry, when you said the top 10 in the time trial, what was that event? What race was that?
That was the World Championships in 2021 in Belgium.
Wow, you got them all in and tested them.
No, that was calculated from pictures where you identify certain anatomic marks, and then you can analyze it. I think that if you Google and we can maybe we can even put it up on Twitter, the link to the paper. Then we took Danish time trialist who finished in that, and then we tried to mimic those positions to say, okay, upright 20 degrees, 12, and down to the 8. And then we showed in that they could reduce from their normal, which were from 8 to 18. And if we reduced that down to 4, they perceived it as harder, but they didn't lose mechanical efficiency. And they already were adapted to quite low positions because they were also they were top 25 finishers from the national championships. So we, so to say, combined some of those. Of course, it would be interesting. I mean, for the record, the winner, which was this big Italian Ghana, he and Remco Evenepoel were the two sitting in the lowest, the most aggressive position. So
Very
that was
different
quite
body
interesting.
types.
Yeah, very different body types.
That's interesting.
But I mean, adapted to this very low position. And you can say, how important is it to sit low? I mean, you can also see some riders choosing. And of course, that will all the time be a balance between how much power do I lose if I go more aggressive compared to how much will I potentially reduce my CDA. And that's, of course, where it becomes, so to say, a state of the art to find that balance and where you can test it and try it. But my point is that if you only test it in an acute position, you don't get the trainability to it, because I mean, it will probably take some kind of training to be able to be stable around the hip, to be able to produce the power in that position. So it probably also takes some training.
So with those, with that study you did, are you actually able to predict their finish time if you know their watts, their CDA, so their cross-sectional area and drag, etc., and their weight and things like that? Are you actually able to predict what time they'll finish in?
It is what gives the best measure. So if you have all of these parameters, and that's what I'm saying is, if I only got your VO2 max, or if I only get your incremental power output from a lab test, I can predict 22% of your power.
Yeah,
if I
but that was a 7K time. But to be fair, if you did like a 1 hour,
for the longer.
Yeah. I'm just wondering, because I got an hour. I just got an hour stuck in my head because we were talking about your 1 hour
but I mean,
record.
if I get your hour, I would probably like to have your some kind of your measure of power output during a prolonged effort and so on. And then you can always say, how much will I lose? If, let's say I knew your average 20-minute power, how much will you use from 20 to 1 hour output and so on. But if I know the environmental conditions, so I can calculate air density, if I know your CDA and body weight and your bike and so on, I think I will be able to, within 1 to 2 kilometers per hour, predict how fast you can go.
That's interesting. So why don't we talk more? I mean, you've done so much research on the effect of temperature, but we've somehow managed to talk about lots of other interesting things. Why don't you tell us a little bit about the effect of temperature? So you said affects the air density, but just other things. So the effect on the cardiovascular function, sweat rates, effect of humidity, all that sort of stuff.
Yeah. You could say I tried to actually develop, so to say, a model where you could say, okay, there's a muscular component. Can it speed up muscular fatigue? And the main player there is probably that if heat hypothermia hits your cardiovascular system, because when you become heated, you will require some of that heat to be transferred to the skin to be dissipated to the environment. And if that part of the blood volume, part of your cardiac output needs to go to the skin, then your cardiac filling will be slightly reduced. You will, over time, as you become, then you can try to compensate, increase your heart rate. But when you increase heart rate, then you also get a shorter diastolic filling time. And if you have less central blood volume, your CVP slightly decreases and your heart rate goes up, then it's, so to say, a negative spiral, and then your cardiac output will decrease. And if you decrease cardiac output, arterial oxygen delivery decreases, and then it affects muscular fatigue. So that's one way around where heat can influence
What about if you're drinking fluid? I know it's hard. Well, it's easier during cycling, but it's hard during running. If you try and drink fluid equal to your fluid losses, again, back to Eddie Coyle's sort of classic
then
work.
You can limit it, because it's quite clear that if you develop hypothermia on top of dehydration, but actually in my master's study, which I did with another of your guests, Jose Gonzalez, which I had. He was my mentor, my very first mentor. We actually showed that if you get very hyperthermic, then even if you prevent dehydration, it doesn't matter. If you become dehydrated, you become less resistant to heat stress. So you will also in practice become faster depleted, but it doesn't matter if your core temperature goes up and your skin temperature is high, then you will get the cardiovascular stress. You will reduce VO2 max. And you can say that is what probably is the most affecting when you do the very intense bouts. But then you could say, okay, again, in a mix where you do lower intensity, highest intensity, because we also see that people get fatigue if they just go flat out 60%. And in those conditions, even though you also there have the decrease in stroke volume, you compensate. So we don't see any change in oxygen consumption, and that was actually the center, of course, of the first studies that I did in my in my PhD, was to show that it actually also affected central fatigue. So in those conditions, it's probably more dominated by a reduced ability when your brain becomes 40 degrees. I mean, there's some interaction with neural function that will not allow you to continue maximal exercise. And you can say, so to say, from a philosophical point of view, you could say, okay, it's the ultimate thermoregulation. If you exercise in an environment at an intensity where you cannot maintain your heat balance, your core temperature keeps going up, you have maximal vasodilation, you have maximal sweat rates. What can you do? You can stop exercising. So you fatigue, or you reduce your heat production. So you can say that's the only way.
Was that Bodor Nelson that did that classic study? I think that she got them in 10 days in a row in a heat chamber.
Yeah.
Exercising to exhaustion.
Yeah.
And they went longer every day, but they got to the same body temperature.
Yes, and then afterwards she did the same, where they actually took them and then they manipulated the starting temperature. And that was together with Jose Gonzalez. And that was at the time when I walked into their lab and became a master student. So on top of that, but I mean, the similar ending core temperature is on the condition where you have similar exercise intensity, you have the similar environmental condition, and so on. I don't think it's a critical, but it showcases that when your body temperature, or especially your central nervous system temperature, gets high, it affects the ability. So my add-on to that was to showcase that that actually had a central fatigue component. So that was some of the first studies that I published back in 2001.
Okay, so you added on to that to show that because that
because
suggested it was central, but you actually
she had a hypothesis, but there was no evidence for it, and that's sometimes what we do in science. We need to have the so to say proof. So what we did was that we stimulated people on their peripheral nerve, and then we asked them to do an MVC, and then we stimulated on top of that, and then we could identify the loss of power output, which funny not do not occur if you only do a short contraction or if you have brief breaks in between. But if you have to sustain the effort, like you probably have when you do a continuous running and so on, then you are not able to sustain the same central nervous drive.
I might just clarify for people. So MVC, maximum voluntary contraction. So basically you get on a machine, you contract your quads usually as hard as you can, and you see what force you produce or torque. And then you electrically stimulate the nerve, and then you get extra. So that's the assumption that the brain can stimulate more force. And then you're saying when they have central fatigue, you don't get much of a, is that what you're saying? You don't get much of a, that's twitching.
So you can say, okay, you can have a decrease in force because the muscle, each action or each myosin action is having a lower force production, or it could be that you have a lower activation of the muscle. And if you want to discriminate, then you need to, so to say, stimulate electrically. And then you do superimposed electrical twitch.
Okay, and what do you get? So when they're fresh, you get a maximum voluntary contraction, and then you do a stimulation on top of it. And then when they're fatigued, they get less of a maximum voluntary contraction. But you're saying when you stimulate it, they get what?
Yeah, so you still get the muscle still fatigues, but let's say that if you have the fatigue pattern and you say, okay, your force decreases, And then you have it in another condition, which we saw in the heat, that it decreases more. But then when we stimulate it on top of it, the force that the muscle could produce were actually similar. So the lower force that we saw in the hot trials were most likely, if we interpreted that, associated with less neural drive and not differences in the muscular fatigue response.
Correct. Because you're twitching it. Yeah, so when you electrically stimulate it, you're cutting out the brain and you're showing that the muscle can still respond normally.
Yeah.
So it's just not getting the messages from the brain as much. The thing I wonder about that, and I guess, again, we're off, something I've thought about along the years, how does that correlate, though, to submaximal? No, because we're talking about submaximal exercise. Can you assume the same thing when you do this maximum stimulation?
Probably not, but I mean, it's the best that we can do. That is, and that's often what we do if we want to understand fatigue. We have something, and then we do a lot of submaximal, and then we do some maximal to assess, okay, the decrease from pre to post was that. And I mean, here we used the most simple. I mean, it's like what we do out in the 6 hours simulated. We do a maximal sprint, we do a maximal 5 kilometer, and then we do something in between, and then we test how much of fatigue is there by doing the maximal sprint or by doing the maximal, so on. And like, of course, you could then say, okay, another way of doing it is to have people do the same and do the to fatigue or assess it to see RPE, is that increasing rating of perceived exertion. So I mean, there are different indicators of fatigue,
but also
very often
EMG, right? You can do EMG and see if you're getting less messages from the brain to the muscle, right?
Yeah, but the thing is, we actually also did that in some of the studies, and it is, as long as you keep doing the intensity, then your EMG signal will also be maintained. Because I mean, if you have to do 60% of VO2 or do a given power output 220 watt, it takes a certain given of muscle activation, and all the way until you stop, you actually have the same EMG signal going out over the muscle. We can see some indications of changing in the EEG. But again, what I would say, I'm an experimental physiologist, and I'm quantitative, so I'd like to have a measure of so to say. But I mean, we see changes in the EEG indicating that you get more slow waves, and some people would interpret that as fatigue. But as Nils Secker used to say, I mean, that's voodoo. I mean, that's religion. You need to have a hardcore output measure, and there the hardcore is, of course, that you can see, okay, that actually also translate into lower muscle activations. So that's why I come in there.
I like that you mentioned rating of perceived exertion, because for a while there, it was sort of like, this sort of old-fashioned concept. But I remember doing my master's with David Kostal. He always said that rating perceived exertion was a good way to get an idea of all the different signals, that are coming in, etc. And I know that
my thing, if I had you exercising on a bike, and at a given time, let's say that you did. I took you into the heat, and I had you on a bicycle. I had you do 200 watts, and I, at a given time, could do only one measurement to indicate for how long could you keep on this exercise. Then I would say that the RPE would be the best measure I could take. It would beat my ability to measure your core temperature, your heart rate, whatever. Because I mean, your heart rate, I mean, I wouldn't know your maximal. How far could you go? Maybe you can even, if you do exercise in the heat, you have a higher maximal heart rate. If I measured your core temperature, I mean, even though we saw that all of these they stop around 40 degrees in central. I mean, some people can tolerate 39.5, others 40.5, some 41. So I mean, still the RPE is not that bad of a measurement. But of course, as physiologists, we like to understand it in integration with some more physiological measurements and so on. But I still think it's a very useful measurement, and I actually use it also sometimes to prescribe training intensities. So when I do tests of I also do some coaching of some younger athletes, and we actually use a test where they do 10 minutes, where I ask them to be blinded to their power output and their heart rate. They can only look at the time, and then they shall write with an effort that equals an RPE of 3 on a 1 to 10 point scale. You also can use the old 6 to 20 and so on, but that doesn't matter. Then I ask them to do 10 minutes on RPE 3, 10 minutes on RPE 5, and 10 minutes on RPE 7. And then you can look at the linear correlation, and it actually correlates quite well, that the increase that they have from each of these steps correlates to their 20-minute power, which is equal to an RPE of around 9 as an equal. And then you can look and you can use this actually to prescribe different training zones. I think it was a concept that was this of using RPE-based training. It's an older concept, but
it's
I mean,
basically you train the way you feel, which is like the most basic thing.
Yeah.
Way
but
before
the
heart
thing
rate
is
monitors
that also if they have done a stage race or they have done hard training, you can see that if there's a suppression of this this relationship. But the thing that I was saying was, when they need to go easy, then I can use the power output of 3. Don't go above that until you have done your intervals, or in between your intervals, don't do that. If they have to have a training session where they need to go with a certain quality, we want to have some cardiovascular stressing, but it should not compromise their day-to-day recovery, then I have them do, let's say, 20 or 15 minutes at the RPE equal to the 7. So using that as, so to say, an integrative of the psychophysiological load is useful, I believe.
Talking about psychophysiological load and rating of perceived exertion and everything, I should mention that we had Sam McCora on here, so talking about central fatigue and all that sort of stuff. So people should have a look back at that. Okay, so a third, you sent a few dot points to me about things we could talk about. Third one was the motor cognitive task. So it sort of fits with what we're talking about. The effects of solar radiation. What did you want to say about that?
Yeah, again, it's one of the things where we in the lab have not been able to mimic real life settings. Because when we do testing, or most of, there has been some where they have superimposed the radiative load that the sun has. So if you go outdoors and you have 35 degrees, you can still receive radiative heat load from the sun. And in a summer day, like in Denmark, outside it will be around 800 watts per square meter. So it's actually a massive load, and in South Europe it can be as high as 1,000. But then it depends on cloudiness. But usually when we do in the lab, we do dry heat. So we just turn up the temperature, and we also manipulate with humidity. But there's not been that many studies that also have. There was some of these studies with Otani and so on. But we started looking into it with a big EU project that I had, Heat Shield. And we did, because we wanted to simulate it better. And then we did some trials where we also only exposed the head, and then we applied a similar load to the lower body in order to compare, do it have specific effect on the heat. And the thing was, and now we are from some of the observations where I still would like to do more studies in order to understand this. I would guess that I have had more than 100 people, athletes, who has been exposed to heat exhaustion. Going to maximal until they say, I need to get out of here, of this room, I can't do anything more, in, you could say, dry, high heat. So 40 degrees, also in somewhere we have used protective clothing because we have been in Nils's lab and so on. So high humidity and so on. And none of these, and it's more than, maybe it's 2,000 cases. I have never had any subjects who have fainted or they become tired. They may say, oh, I'm almost, and then they go out of the lab, and then some of them lie down, but all of them, they recover quite fast. Then we did these trials with the superimposed radiation. 3 of the subjects, some of them very experienced. One of them was a PhD student I had from Cyprus. They fainted. So this radiation effects, whether it's the thermal part of the radiation, you have different wavelengths, and it's actually the visible lights which has the biggest thermal density. So out of all these 1,000 watts, some of it can be ultraviolet, some of it can be infrared outside the visual spectrum, and then you have the visual light that has the biggest thermal. Whether it's that, when it penetrates the skin, whether it causes massive vasodilation, release of NO that interferes with your ability to
Glad you said
regulate
that.
your blood pressure.
I'm glad you
Whether
said
it's
that
that
because
effect or it's the UVR, the beta lengths, which has specific effects. We know that if you get very high loads of that, it can cause DNH damage in the skin, and maybe also the release of some of these substances can go in and affect your cardiovascular function. And there we actually miss a point where we don't know why it is, but it could explain why is it that athletes, we see that quite a lot, they faint in the heat. We see people getting dizzy, workers, and so on. And that is one of the things that I think that we haven't been able to understand well enough. So we actually described a project now that where we want to look at this both in high and low tolerant, and we want to actually combine to understand the interaction between the ultraviolet exposure, which we know have specific effects on melanocytes in the skin when you get brown. I mean, it's not the temperature. If you go to sauna every day, you don't go brown. That's the UV, the spectra of the radiation. And we want to understand that interaction, because I think that could shed light into some of the observation and again, some of this lack of transfer from the lab to the real life.
So you're saying that we've all seen athletes exhausted and wobbling all over the place at the end of like a marathon and things, and they do actually faint, I guess you're saying, and you never see that in the lab. You exercise people at 40 degrees, thousands of people. You never see someone faint. Is that what you're saying?
Yeah, especially when they keep exercising. I mean, when they stop, I mean, their sympathetical activity may be reduced. Then some of them, so on. But then we take them out, and there's no problem. I mean, here it was literally we had to drag them out of the lab. I don't know if we can tell this to the ethics, but I mean, it was approved by the ethical committee that we could have people. And I mean, it was even at the court. I mean, I should say, when we did this, where we exposed the head and the lower, it was even if we exposed the lower body, and it was at a core temperature of 38. Whereas in all of these other conditions, we typically see that people get to 40 degrees. So again, it occurred at very low levels of internal body core hypothermia, if you would say to say. So I think that this radiation has a massive effect on. My hypothesis right now before it would be that it is NO release related to a very high effect on the skin.
Nitrite. That's the interesting thing, because I was when you said nitric oxide, because that's for many years was my main area, and I saw somewhere that it said ultraviolet light, I think it was UVB, causes nitrite to be converted to nitric oxide in the skin. And that potentially that's why people that live near the equator have lower blood pressure at rest and things like that. So are you actually thinking, is that what you're thinking, the nitrite?
Yeah, that's the line of that could be very interesting to systematically explore, and to explore the interaction between the pure thermal effect and then the UVB radiation.
So people are clear on this, is nitric oxide actually, in 1998, the people that worked out the cardiovascular effects of nitric oxide won the Nobel Prize. So nitric oxide is a dilator, just so people at home know, that's produced by endothelial cells in the blood vessels, and causes relaxation of the blood vessels and drops blood pressure. And you're saying that may actually be going on because the sunlight is causing, is that the UVB? Is that what it is? It's causing the conversion of nitrite to nitric oxide. Yeah, that's very interesting.
And we work together with some people over at dermatology, and they can actually mimic everything from UVA to UVB to UVC. But the best guess is that it's the UVB spectrum.
And just to clarify, so you're saying these people's body temperature is only 38, which is like not even really raised from
in passive it's high. So that was.
But are you exercising them? And
no,
so,
in this
so they're just sitting there.
Yeah, in this condition. Sometimes we use a combination of higher thermal environmental load and then internal, because I mean, it's just like
if you've done the exercise and added the ultraviolet, have you added the radiation to exercise? Have you done that?
We also did that in some of the studies in Greece and so on. And the thing is, we get much better models, both in predicting loss of productivity, but also in exploring the effect when we add the radiation. So I think that neglecting, or you could say missing the part from radiation in lots of study, also in acclimation studies. And it's quite amazing, actually. There's never been any systematic acclimation studies where you have exposed people to a given level of sunlight simulated exposure consecutively over days to see if that maybe lower your release of nitric oxide from the skin vasculature, and to see if that makes you more resistant to this. So, I mean, we have a large tradition for making, you could say, thermal heat acclimation studies, but actually none in the aspects of radiation.
Like, no? I guess the whole time you were talking about the radiation and people fainting and things, I assumed you were talking about with exercise, but you're talking about most of the studies you've done are at rest, and you add the radiation and people get faint. Is that what you're saying? Yeah.
We did that in the resting condition. Maybe they will still be avoided in if they keep exercising. I mean, because as long as you keep exercising, your blood pressure is a little higher and so on. But I mean, again, in real life, you always have a mix. Then you do some exercise, then you have resting period, and
it's funny because it actually reminds me that there used to be a guy when I was a runner that I'd race against, and he'd often wear like suntan lotion, but even more like just like putting patterns on his face, different colors and all this sort of stuff, and all over his body and things like that. And I was thinking, I wonder if that affects his sweat. I wonder if putting suntan lotion on affects his sweat.
Yeah, but again, another one that you will not. Yeah, but again, if you only acclimatize by, you could say, artificial exposure in the lab, and then you go to real life setting, then you would need to put on a lot of sun lotion to protect your skin. And maybe that could then, I mean, at least if you have a very thick layer, it could impact your thermoregulatory capacity.
Yeah. So does it actually affect you? It have to affect your sweating ability, right? If you've got this chunk of
or the evaporation, because I mean, it's not the sweat has to evaporate before it has a thermal regulatory effect.
Of course. All right. So I just thought I'd go to there's some questions on Twitter you may have seen. So here we've got a guy, Pao Marino, who often sends good questions through. It's asking about, are heat adaptations specific? So if you're doing adaptations to heat, humid versus hot dry versus humid, I assume, also passive versus active. Do you have any thoughts on that?
Yeah. Basically, you could say, okay, back to the idea that a sweat gland sees a given response, and I mean that is dependent on the neural drive that it gets, which is affected by your central core temperature, and then it's seeing some local temperature. And it's quite clear that if you have, let's say that you dress up in a clothes, or if you have very humid, then the local tissue temperature may be slightly higher. But again, the central core temperature will be probably the same. So I would see from a physiological point of view, there's not much difference. So if you do it passively, you do it by exercise, you do it in hot, humid, and so on, your physiological adaptations will be, I don't see a big difference there. But so then there was this sweat, with the, but then it would be that if you, but what happens in humid condition is just that the sweat drips off, but the physiological response, the activation of the sweat gland is still high. You will not see the same benefit from it. So of course there can be slightly differences between that. In very hot, humid conditions, you will rely a lot on a high skin blood flow because you don't have the same efficiency of the sweat, so that's dripping off, so your skin temperature gets very high in humid conditions, whereas in dry heat you can keep your skin temperature lower for a given temperature.
So of course there can be active.
Again,
you're getting all the cardiovascular adaptations with the passive, like if you're exercising, I guess, versus just sitting around.
Yeah, but also in passive conditions, your skin blood flow becomes higher, so there could be slightly differences there, because it's when you exercise, you don't increase your skin blood flow to the same level. But again, basically overall, we've done some studies where we have exposed people, and the responses we see, whether it's dry heat, natural outdoors, acclimatization studies we did in Qatar, whether it's in the lab where we have done it, you can thermoregulate, or we have done it in some sweatsuits where it simulates actually wet conditions because you cannot evaporate the sweat, so you get very humid in under this sweatsuit. We see the same. You increase your sweat rate, you lower your sweat natrium, you increase your plasma volume, and if you do it a long time enough, you also increase your hemoglobin mass. We see similar improvements whether we do it in climate chambers or we do it in the sweatsuit. So I don't see a big difference there.
Okay, great.
But again, with natural exposure, the thing that you will gain is that you also will gain the adaptation to the UVB. So you also get that part of it, which you will miss if you do it in the lab. Also, the learning effect to see, okay, how much do the specific environment affect me? That's better with the natural exposure. So that's where it has an advantage.
Another question he had, which actually reminds me of me riding my bike indoors, is training indoors a good training for heat adaptation? So it occurred to me at one stage, I was always turning on the fans. I'd be riding, like I've got a Wahoo kicker and Swift and all that stuff. Yeah. And for a while there, I was turning on the fan and I was like, hang on, I'm hardly even like sweating here, because I'd always be sort of, just when I was riding easy, I'd be sort of matching.
Sweating, but it was evaporating.
That's true. But what I mean is I didn't really get hot. I wasn't like hot and bothered. And I thought, hang on, this is making my training bout. So if you're doing 150 watts, for example, if you turn on the fan and you're not really getting hot, it's obviously easier than if you don't turn on. So then I was thinking, well, on my easy days, maybe I should just not turn on the fan to make it a bit harder, but I'm not, maxing my muscles.
But I mean, indoor training will stimulate it. I mean, on top of that, we also use, when we want to have heat adaptation, we actually also have some clothes on. Because I mean, if you do 150 watts, your endogenous heat production will not be enough to surpass your dissipation capacity. But I mean, if you do it very intense training in, let's say, indoor, and it's 20 degrees and it's still air, then you will get some significant heat stress. So I mean, if you do regular these indoor competitions on Swift and whatever platforms it's called, I mean, you will probably get some heat adaptation. But I mean, we use it indoor training, extra clothes on, that can produce massive heat adaptation. We have used that in particular because, I mean, if you live in Denmark, it's only hot in 2 months in the summer period, so you won't get heat acclimatized. And we used heat acclimatization because we've seen that can actually also drive up your hemoglobin mass. We have quite good evidence across a broad spectrum of studies that you can increase your hemoglobin mass by 3 to 4% by becoming heat acclimatized. But it takes more than 4 weeks, I would say, of heat acclimatization. Okay. So these short terms, 1 week, 2 weeks, which was the old day, is not enough, because it may drive up your plasma volume, but in order for you also to have that translate into increased erythropoiesis, I mean increased HB mass, our study shows that you should probably, 5 weeks is probably sufficient in all. We may also see, I mean, between 3 and 4. So in this question about if it also translates into improved performance in cold, I would say in cool to natural environments, probably yes. You can have benefits, so you can at least have physiological adaptations that are meaningful in terms of increasing your hemoglobin mass.
That's true. So yeah, one of the questions he had was, can heat adaptation, acclimatization improve cold? And you're saying because it's giving you some of the stuff you need anyway for having a higher oxygen delivery by having increased hemoglobin.
So what we see is that it can increase your hemoglobin mass by these 3 to 4%, and it can increase your peak power in cycling incremental test by some 15 watts or something, which is meaningful. But we typically don't see that it can also increase your power output in time trial, like indoor simulated and so on. But usually that improvement is not significantly different from the control group, because I mean, it's difficult. You always have a control group and they will not stop training, and you can see it in a training camp. But then you could say, on the other hand, as we discussed, much of outdoor real life is fluctuating. And then you could say, okay, if I have a higher peak power, then it would be meaningful. We don't usually see that it also translates into significant, but again, it could be the noise to, because it's not, people always think, oh, it sounds so exotic. You can go to altitude or you can go on heat training camp and then it can increase and all the good they do it. But it's not like you get a 50% increase in your power output. If you have trained athletes doing whatever intervention, it is what in the old days were called marginal gains. But any gain in a trained athlete is a meaningful increase.
Absolutely.
And we now in total have more than 100 subjects. And if we combine all of these results, it does translate into increased peak power.
That's very interesting that heat adaptation increases your hemoglobin mass, because I remember during my PhD, we had this student, Carolyn Burge, so I was with Mark Hargraves, and they were using the carbon monoxide rebreathing technique to get the hemoglobin mass. And it was a classic because we had one guy in there who was training for an Ironman. He had the lowest hemoglobin and hematocrit when you just measure it. You take a sample, right? Because that's per 100 mils, for example, for the hemoglobin. Yeah, the concentration, he had the lowest. But when we did the hemoglobin mass, he actually had the highest. And we just assumed that was because he had a massive plasma volume, that it was diluting the hemoglobin. But you're saying you would also have, which is true, of course, but you're also saying that you actually get an increase in your hemoglobin mass as well.
Yeah, but of course, if that's then diluted into a larger plasma volume, then you get a lower concentration. But it's very difficult because if you have to control and when do you measure people their plasma volume, then they drink some water or they are exercising a little bit more, and then it can fluctuate and so on. But at least the hypothesis from Carsten's and my side when we started initiating these what we call prolonged heat acclimatization studies was that what we have seen in altitude was that if you are only there for 14 days, it's not sufficient time for the increased erythropoiesis, production of new blood cells to mature. So it took more time. So therefore, we tried to expand this period, and then it shows that it actually translates into. It's not as much. If you go very high in altitude, you can get more than. But if we take a normal training altitude camp where people go to, let's say, 2,500 meters, and they stay there for long enough, then typically we would see that people get like 30, 40, 50 grams extra of hemoglobin. So that's equal to what we can get here. But if people go to Himalaya or they stay 1 year in high altitude, then they can have more increases in their hemoglobin mass. So you could say altitude, but altitude likewise, and there I thought that there was a question from this guy also needs that you have sufficient time and it's profound enough. So if you go to altitude 1 day a week, and then you stay at low land, and then you go there another week, then you will not get the hematological response. You may get used to the altitude, and therefore on some of your hikes benefit from it. But if you want to have an effect, and that's the environmental exposure, it takes consecutive exposures and it needs to have a continuum. So if you are not exposed, it's like with training, if you don't train regularly, your training effect will disappear. And then you can always say, okay, how much is enough? But if you only do it once a week, it's not enough to induce the significant hematological response. It may be, and again, it's something we haven't explored that much, because if you go to altitude, there are two components. One of them is again the hematological. The other component is the ventilatory drive, that you will benefit from having an increased ventilation and therefore better defending the drop in oxygen saturation. But my best guess would be that if you go there only once a week, it's not sufficient.
So it's interesting just to tie it together with what you're saying about heat acclimation. So both of these are increasing hemoglobin mass, and it makes sense.
But by two different
exactly.
By two very different mechanisms.
What's the mechanism? Yeah, so I guess we know the mechanism at altitude. You have a drop in partial pressure of oxygen, and your kidneys release erythropoietin, so EPO stimulates red blood cell mass. What is the mechanism? What are the mechanisms in the heat?
We're not sure, but the philosophy was that it increases your plasma volume, and then the body, tries to normalize that to some extent. I mean, it's just like with training. When you start training, you get an increase in plasma volume, and then you also start to stimulate erythropoiesis. On the other hand, we try to measure blood samples throughout, and we cannot measure an increased response in reticulocytes or neutrocytes. So we cannot, I mean, the blood cells has to come from somewhere. On the other hand, if you have a trained athletes, then they have around 1,000 grams of hemoglobin, and the average living time of a red blood cell is around 120 days.
20.
So that will imply that you're in balance if you produce 8 grams of new hemoglobin, and then you break down 8 grams. Then you can say, okay, if you go to altitude or you start heat training, then let's say that you start producing 9 grams or 10 grams. And then if you do that for 3-4 weeks, then you get these 40 grams extra. Makes sense. But on the other hand, can we measure these 2 additional grams that you produce out of a total of 1,000? And it's probably below the detection level of what we can measure as a physiological meaningful response.
So the reticulocytes you're talking about, these immature cells that are the new red blood cells, you can't pick those up.
No, but I mean, it has to come from somewhere. But we can't measure that it
Maybe
increases.
Can't pick it up.
But I mean, again, if we could have 100 or continuous monitoration over the day and so on, maybe we could pick it up. Maybe it occurs after the training session, after the heat exposure session, and so on. But we can't see that it relates to increased HIF, hypoxia-induced factor. We can't see that it relates to increased EPO, and so on. So again, really? the mechanisms are at this point speculative, but my best guess would be that it's similar to an exercise response, that you increase your plasma volume, and then the red blood cells to some extent follows. But it is fascinating. We have had athletes, look at these athletes, they've been training for 10 years. They have a blood volume, some of them 8 liters, some of them 9 liters. And then we heat acclimatize them, and then there is actually room for an additional 300-400 milliliters of blood.
Wow, even from 8 or 9 liters.
Which isn't stimulated if they just keep continuing their training. So
just make sure people are clear on all this. So normally, normal blood volume in a 70. Well, unfortunately, it's always a 70 kilogram male that's in all the textbooks. So sorry, we're not thinking about, not considering the blood volume in females. But a 70 kilogram male, we usually say about 5 liters. You're saying these well-trained, very well-trained athletes have 8 or 9 liters of blood volume.
Some of them. I think that on average, the latest study that we've done, they had on average 7 liters or something like that.
7 liters, so 2 liters. And just to
make some of the individuals have above 8 liters.
Yeah, so make sure people are clear on this. So when we talked about hematocrit and hemoglobin, so hematocrit is the percentage of your blood, which is red blood cells. And naturally, if you increase your plasma volume, which is a major thing that happens with endurance training and exercise in the heat, you increase your plasma volume more than your red blood cells. So your hematocrit drops, and your hemoglobin, which is usually measured per 100 mils, that's going to drop as well. So then people race off to the doctor, and the doctor gives them iron tablets and things like that. When in reality, if you measure their hemoglobin mass, it's probably increased,
which is the total
example I gave. Yeah, exactly. And that's what's important for delivering oxygen. How much hemoglobin mass you've got.
Also probably because we measure it at rest, but what happens when you start exercising is that you actually squeeze some of the plasma out into the interstitium. So then you have the red blood cell remains. So actually, if you and I walk out the door, our hematocrit will increase slightly because we excrete some plasma. And then you could say, okay, in an exercising conditions, then maybe we'll benefit from the higher total volume, although I mean, if you then, because I mean, at the end of the day, it will be the product of the stroke volume, the heart, and then of course the concentration of red blood cells, on the premise that all of them are oxygenated.
Okay, well, this has been great, and we'll probably start thinking about wrapping up. But Mark asked about urban infrastructure and active cycling. So I don't know if you saw that one. So evidence of urban infrastructure promoting active cycling. Do you have any thoughts on that? So being here in Copenhagen, I just love it. It's my 4th time here. Just everyone just riding to commute and riding for fitness and just riding like it's normal. a lot of cities in the world that is not the case, including in Melbourne, where I almost get
Yeah.
cleaned up every time I used to try and ride to work. What do you think? How are we going to roll that out? Should future mega cities be structured like Copenhagen, Tokyo? I think the answer is
Yeah,
probably
and you can
yes.
say I
Bruce.
even complain that in Copenhagen we don't facilitate it. I mean, sometimes we have good infrastructure and people cycle, and I mean it's massive for public health. Then you have the electrical bikes. It's a catastrophe. I mean, no, because I mean people think, oh, I'm doing
It goes
some
so
exercise,
fast.
but in the other way,
Mm.
no. But also what happens is that instead of going, let's say 25 kilometers an hour or 20 or whatever, go slower. I mean, but they still do, let's say on average 150 watts. They get a cardiovascular response. They do their metabolism. Then they go on their electrical bikes and they reduce it. They only do half or they do nothing.
Mm-hmm.
And I mean, they are cheating themselves. And I mean, we had this discussion about public health and why do the pollution or the population get fatter and unfitter. And I mean, at some point, we got to ask ourselves, both as humanity and as individuals, when is it not our own fault? When we don't take the steps, when we use an electrical vehicle, whether it's these scooters that you can stand on a bike instead of doing your bike. I mean, we get more and more passive. And I mean, of course, if we want to facilitate that, you could say the infrastructure, but whatever it makes that, and I mean, in many years, Danes had higher cardiorespiratory fitness than example giving countries around us because we were bicycling. And I think even in Denmark, even if you as foreigners think, okay, the infrastructure here is good, it's still the percentage of people communicating by bike is decreasing. And I think
Is
that's
it?
going to that's going to affect public health.
Shit.
So yes, I'm a fan. Whatever you can do in order to facilitate this, but I mean, in some points we are moving further and further away from what is, so to say, healthy for us as
I didn't realize
as
there was
humans.
less. Maybe it's all the tourists that are out there riding their bikes because I didn't realize there's less.
No, but I mean,
riding.
then it's also good in Copenhagen. But I mean, there's still also a lot of people sitting in their bike. So whatever we can do in order to stop, you could say, the trend of making people more passive, and then you could say, okay, all of the infrastructure. But I mean, now we're getting political. If we really were, I mean, there's this Dutch city where they only have, there's no vehicles. I mean, what if we in Copenhagen said within certain area, you can only have, I mean, of course you should allow transport to get goods in and out of the city, and you could also have something. But what if we could do that? I mean, if we could have an entire city where all of the infrastructure were based either on people walking, vehicles, or public transport. I mean, we could facilitate this even more, even if it's good. I mean, if the politicians dare to do that.
Well, it's interesting you say, someone said to me, we had this friend over the other day, and he said that electric bikes, they don't work if you don't pedal them at a certain wattage or something. Is that right?
Some of them, I guess. But I mean, have you seen some of them? Some of them, they are as big as a cross motorbike. I mean, they will weigh 100 kilos and they can go 40 kilometers an hour, even if they don't pedal. On some of them, you have to do a little pedaling. But again, it's quite clear that if you have a power output which produces you with 200 watts or 250 or 500, as some of them can, then you will do that less.
Exactly.
Exercise
and indeed, so when I first came here in 2013, I don't think anyone was really, there wasn't really such a thing as electric bikes. But now a lot of people say, well, this way I can ride to work and I don't get sweaty and things. So by definition, they're not doing as much work. Yeah.
No. And you could also say that if it substitutes for you driving in a car, fine.
That's good.
But people call it a bike. It's not a bike. It's a small electrified motorbike. And some of them even big. So that's my take on that. So, but as a human physiologist, I would think that it's counterproductive to the training effect that many people would get out of their natural transport to and from work.
Mm-hmm. Oh yeah, and the other thing I think is I often assume in Copenhagen here that this is Denmark, and people say, well, you can't assume it's not Denmark, it's Copenhagen in terms of how many people are riding their bikes. Naturally, in the countryside and smaller cities, they wouldn't have the infrastructure.
Yeah,
exactly. Okay.
I biked to school when I was a kid, so even from there.
Good man. All right. So what I'd like to do at the end is, can we do some sort of takeaway messages? So I guess we've had a lot of interesting chats, but the main focus, I guess, was your saying that you can't always, what you get in the lab is not always that transferable to real life. Did you want to just finish up on that?
And for some of the young upcoming physiologists out there listening to this, always be aware, do I actually mimic, and what is it that I can take, whether it's actually something where we try to mimic it. I mean, that's what we do when we do environmental physiology. We want to mimic the real life settings with the exposure, but also, and especially if you go into, you are doing in vivo studies and you're doing cell lab and so on, try to put it into the context of how is it that I translate this knowledge into real life and mimic your protocols to say, okay, I want to understand what is going on in real intact humans doing work outside. So that should be the ultimate goal. Of course, then that can be balanced up against your desire and need to be able to control the settings. Because when we go to the aerodrome and do the testing, of course, we are relying on that we can control conditions sufficiently. So let's say that the change in conditions are so big that they screw up your experiment. Of course, we shouldn't do that. On the other hand, we will gain something by doing more ecologically valid testing. And that is also in terms of whether it's continuous or intermittent protocols and so on for cycling, testing, training, etc. So I think that's an important. And then also the thing back, if there's a model or if there's a zone or whatever it is, and it's human derived, that we take a given score and intensity, always try to translate it into see what is the stress that your body sees from a cellular perspective. What stress do the brain see? What does the heart see? What about your blood volume or your muscle? I mean, try to break it down to that to see, okay, it has this effect. So can your whatever score predict that? Or what are the limitations for it?
Great.
I mean, your body don't know the zones. I mean,
that's great advice, and it's good advice. What you said about thinking about whether your model matches real life, that's exercise or anything, any sort of research.
Yep.
When you're doing cell culture or mouse studies or whatever, how does this relate to a human?
Yeah, I remember in some of the old studies, they always saw that mitochondria, they were disrupting, or they were breaking, or they were not functioning at 38 degrees. And then I would say, okay, an athlete, then they wouldn't have any functioning mitochondria left. I mean,
that's true.
Because what they were able to mimic in their cell cultures were not real life relevant.
Sorry, one thing before I let you go, I always do this. I always think of something after we've done our takeaway messages. You said something I wasn't aware of, that maximum heart rate is higher in the heat. So if you did like a max test, for example, really?
Yeah, we saw that systematically, that it was 3-4 beats higher when people were hypothermic. And maybe it's in a trained population, but there could be two parts of it. One, the sinus node is temperature affected. So in any cell, I mean, you could say depolarization, every flux of ions across a cell is temperature dependent. The other thing could be that when you have a lower stroke volume, then you could say, okay, the baroreceptor reflex. Whenever you have a stroke volume, then you will also have a pulse curve. And of course, if that gets high, and then if you have, when you're heat stressed and your stroke volume goes down, then the pulse curve decreases, and maybe that has an effect through the beta or the baroreceptor reflex. So I think that would be probably
very interesting. So that's not just doing like a max test in the heat. You're talking about if you've got hot.
No, we're talking about we did a max test. When you are doing a max test in a hypothermic state, then you get a higher peak heart rate than if you do it in a cool condition.
even when you haven't dehydrated them first. You're talking about the straight
Yeah.
one.
If you dehydrate on top, you get an additional 2-3 beats.
Okay, cool. Well, hey, thank you very much. And I'll probably see you in the corridor like 50 meters away from here afterwards.
Yeah, that would be funny.
Good on you.
But
Thanks.
this is the way that we get out to the world, and it was great chatting to you.
It was great. Okay, good on you, Lars. See you. Bye-bye, mate.
Yeah, bye.
Bye. I hope you enjoyed this podcast. And please like, subscribe, pass it on to your friends and colleagues. Check out the other podcasts. Thanks again.